This is Zuzanna, a chemistry student at East Tennessee State University, and today we're going to follow her as she completes a single crystal X-ray crystallography experiment. Safety is her and the university's first priority when conducting laboratory experiments, so as she enters the lab, the first thing she does is put on her lab coat. Next, she takes a seat at the workbench, where she'll begin by selecting a sugar crystal. Last night, Zuzanna made sure to familiarize herself with the experiment by reading through the instructions for this lab provided to her by her instructor. She also brought a printed copy of the instructions with her to the lab so she'd have them to reference while completing the experiment. If you have a copy of the instructions for this experiment, now is a good time to retrieve them so you can follow along with Zuzanna for the remainder of the experiment. Zuzanna begins by preparing her workspace. She selects a needle and dips it in some APA-zone grease. The grease will help crystals stick to the needle, but only a small amount is needed. Next, she opens a packet of sugar purchased from a local grocery store. She pours a small amount into a petri dish and places the petri dish on the stage of the microscope. Turn the microscope main switch on, turn on the lights, and adjust the magnification knob to the lowest setting. Next, search for a crystal that is between 0.1 and 0.3 millimeters in all directions. Now, use a needle to pick out a few promising crystals. Use the microscope to help mount your crystal on a fiber. Set it aside in a safe location, and then turn off the microscope. Zuzanna is now ready to scan her crystal to determine its quality. She begins by selecting the appropriate version of CrysAlisPro. In this case, she's using version 40.67a. Once the software is fully loaded, click on the Start/Stop button in the top right-hand corner of the screen, and then click Start New to start a new experiment. Enter the name of the crystal experiment in the name field. Be sure to include your initials, the name of the compound, today's date, and the corresponding page number in your lab notebook. Go to SM Screening and then click Mount. Press the door lock button on the diffractometer. Wait for the flashing light and beep, then open the X-ray diffractometer door. Although the X-rays are on, the shutter is closed and you will not be exposed to any harmful radiation when you open the door. Next, carefully place your mount on the goniometer. Use the Allen wrench and the inverted CCD cover inside the diffractometer to adjust the crystal until it is in the center of the circle on the screen. On the screen, there are 4 buttons you can use to change the angle. Drive the angle first to 270 degrees, where you can adjust the height. Once the goniometer stops moving, return to the diffractometer and use the Allen wrench to adjust the height and center the crystal. Only adjust the knobs that are facing you, unlike what Zuzanna is accidentally doing here. Adjusting the other knobs could knock the diffractometer out of alignment. Here, Zuzanna has corrected her mistake and is now adjusting the knobs properly. Now that the crystal is at the proper height, center it at the remaining angles, and then replace the Allen wrench inside the diffractometer. Close the diffractometer door and exit out of the camera window. Back at the console, under SM Screening, Click Edit. Once the pre-experiment menu comes up, click Set User. Since this is Zuzanna's first time completing an experiment using the diffractometer, she'll need to add herself as a new user. She types her name in and then clicks OK. Next, set the exposure time. Typically 5 seconds is sufficient for a sugar crystal. Weakly diffracting crystals, that is, small crystals, or crystals of poor quality, typically require longer exposure times. In the expected chemical formula field, enter the chemical formula for sucrose, C12H22O11. In the comment field, enter the name of the compound. Check that interactive strategy after pre is checked, then click Exit and start pre-experiment. The pre-experiment is where the crystal is evaluated for X-ray quality. The shutter is open when the shutter close button turns red and reads Shutter Open. After the exposure is complete, you should see peaks, or spots, appear on the screen. The peaks correspond to areas of high X-ray intensity. Once the pre-experiment is complete, the experiment strategy screen will come up. First, record the unit cell data and the lattice data as Zuzanna is doing here in her lab notebook. Sure the resolution is set to 0.800. Check to make sure the Friedel-Mates box is unchecked, because sucrose is chiral. Next, change the exposure time for the experiment to 30 seconds. A 30-second exposure time will usually result in an experiment duration of 4 to 6 hours. If you would like your experiment to conclude faster, you can set the exposure time to a lower value. Just keep in mind that you'll get lower quality data. Next, make sure that the IUCR limit is set to 100% if possible. Click Calculate New Strategy and then Update Completeness. You will be given an estimated completion time for your experiment. If the completion time is acceptable to you, click Start Named Experiment to start the data collection. A window will come up where you can review that the user and the name of the compound are set correctly. If both look correct, then click Start. Before the experiment begins, CrysAlisPro Online will take a short movie of your crystal, shown here in time-lapse. Once the data collection begins in earnest, notify your instructor. This concludes the first part of the crystallography experiment. Good morning. It's been a week, and Zuzanna has just arrived at Brown Hall. She's on her way to her practical crystallography class, where she'll have an opportunity to review the data that was collected during the experiment she set up during her last class. Once in the lab, she retrieves her lab notebook and prepares to review her data. Zuzanna begins by first checking to make sure the diffractometer is not actively collecting data. This is done by checking in the upper right-hand corner of the screen to make sure CCD and RED are both ready. Next, click through the tabs to acquire and record needed information. beginning with the Crystal tab. Record the lattice unit cell information. Next, click on the Data Collection tab. Record the frames and runs to do and the number done. Then record the start and end times for the experiment. Under the Data Reduction tab, record the completeness, record the number of outliers, and record the space group. We are now finished with CAP Online. Close CAP Online by clicking the X in the upper right-hand corner of the window. Click Keep Generator Settings unless your instructor tells you to do otherwise. Next, on the desktop, find the designated version of CrysAlisPro Reduction, or RED. Double-click on it to open it. Once it opens, a window will come up with a list of experiments. Select your experiment from the list. Then click Open Selected. In the bottom toolbar and to the right of the play button, there is a small drop-down arrow. Click on the arrow to change the speed, slowest best, and then click the play button. Review the data set for bad data. Examples of bad data include peaks where one peak is on top of another such that the spot appears oblong or hourglass shaped rather than circular, and abnormal rows of peaks. For example, parallel rows of spots with one brighter than the other. When you're done reviewing the dataset, click the Stop button in the bottom toolbar. Now it's time to add the beam stop mask. First, click on CMD, which is located on the left side of the screen. Select Options Red, then click Beam Stop. Select Put Beam Stop Overlay On. Adjust the beam stop parameters so that the beam stop and line are covered. To adjust the beam stop, manipulate the diameter and angle values until the beam stop overlay covers the entire beam stop, but as little of the rest of the optical field as possible. Next, return to the Beam Stop tab. Unclick Put Beam Stop Overlay On, and then click Save to PAR File on Exit. Click Yes when it asks you if you want to proceed, and then close CMD. In the upper right-hand corner of CAP Red, there is a button labeled Start Stop. Click this button. A pop-up window will appear. Select Automatic Data Reduction from the list. Data reduction will be done when RED is ready. Once the data reduction is complete, write down the new unit cell parameters. We're now ready to solve our data set. We begin by selecting OLEX2 from the left sidebar. Click the button for OLEX2 one time. Note that depending on your system, it may take up to 2 minutes or so for OLEX2 to fully load. Once OLEX2 opens, make sure the file that it loaded is correct. You can confirm this by matching the data you copied in your notebook under reviewing your data to the file name in the upper right-hand corner. Also, make sure the title of the experiment is correct. Now, click on the Work tab. Make sure the unit cell data is imported correctly. Click the drop-down menu next to Solve. Typically, Shell XT with intrinsic phasing is the best program to run. Make sure the other parameters are correct, and then click Solve. OLX2 will make an attempt to model the atoms within the unit cell of your crystal. Once the model appears, to rotate it, click and hold down the left mouse button as you move your mouse. If you want to zoom in and out, click and hold down the right mouse button and move the mouse. Now, identify the atoms as either carbons or oxygens. Carbons are gray and oxygens red. You may find it helpful to search the internet and download a model of Sucrose, which you can compare to your own model, as Zuzanna is doing here. If you have a particularly good data set, OLX2 may have identified all of the atoms correctly. If you need to change an atom, however, right-click on a sphere, scroll down to Type, and select either C or O. Next, click on the Refine drop-down menu. Select Shell XL and least squares. The first model the program gives you will treat all of the atoms as isotropic, that is, as a sphere. Click Refine. OLX2 will attempt to refine your model in 4 cycles and will give you a picture that shows possible atoms, bonds, and bond angles. After this initial refinement, it's a good idea to check that all the atoms are still correctly identified. An easy way to do this is to check the bonds. An oxygen atom, for example, should never have more than 2 other atoms bonded to it. Also, notice and pay close attention to the data parameters in the upper right-hand corner of the screen. 3 of particular note are the R1, WR2, and shift values. R1 indicates how close the model matches the data, and what we're aiming for is a figure ultimately that's less than 5% after the final refinement. WR2 indicates how much data has not been modeled, and we're aiming for a figure that's less than 15% after the final refinement. Shift compares how much the data moves between the previous and current refinement cycle. Every time you click Refine, the shift is going to change. What we're aiming for is a shift as close to 0 as possible after we make any changes to our structure. Click on Refine and observe any changes in the data parameters that indicate how well the model fits the data. Continue to click Refine until the shift value begins to stabilize. That is plus or minus less than 0.004 and highlighted in a deep shade of green. If the shift value does not drop to 0 or starts to increase, please contact your professor or instructor, as this may indicate a problem with your crystal or your model. Once the shift value has stabilized, click on the Anisotropic button. Click Refine again. Continue to refine until shift is minimal or 0. The gold spheres you see represent electron density not modeled. The next step in modeling our molecule is to identify the hydrogen atoms. Keep in mind that sucrose has a total of 22 hydrogen atoms. So some of the gold spheres that you see are in fact hydrogen atoms. To determine which ones are hydrogen atoms, left-click on a gold sphere you think is an atom, then right-click and select Bang to see the distance to the nearest atoms. If the distance to a 9 hydrogen atom is between 0.8 and 1.2 angstroms, right-click on the gold sphere, select Type, and identify it as a hydrogen. Each time you identify a gold sphere as a hydrogen atom, its color will change from gold to white, and a new bond will appear between the hydrogen atom and the nearest atom to which it could be bonded. So that's either going to be to the nearest carbon or to the nearest oxygen. Once you've identified as many hydrogen atoms as you can find, click on Refine until the shift value falls close to 0 and the box turns green. Note that new gold spheres will appear. Continue identifying the gold spheres that are hydrogen atoms until you have identified all 22 hydrogen atoms. After you are finished, click on Shift until it stabilizes. Once all atoms have been identified, check the boxes next to weight and EXTI or extinctions. Keep refining the data until shift and weight turn green. Record the final R1 and WR2 values and all the data into 2 green rows in your lab notebook. If you would like to add labels to your atoms, go to the Draw tab. Using the drop-down menu, select Non-H next to Label. This will label all the non-hydrogen atoms. Change the atom names as required by your instructor. To do this, double-click on the label to open a box that will allow you to type in a new label. Do this for all the atoms. Note, before you start renaming atoms, it is best to rotate the molecule so you can see all the non-hydrogen atoms at the same time. Before you move an atom label, it is best to rotate the molecule into the view you want for your finished figure. With our labeling complete, we're now ready to move on to the final step, printing a molecular picture. Our final step is to print a picture of our molecule. To do this, rotate the molecule so that the 5 and 6 membered rings and hydrogen bonds are easily identifiable. Next, change the label locations. Sometimes a label may be located far from an atom or between 2 atoms of the same element, making it difficult to determine which atom the label is referring to. To change the location of a label, hold down the Shift key and drag the label where you want it to go. Note that you may need to rotate the molecule to make sure the label has in fact been moved to where you want it to go. Next, under Bitmap Images, set the parameters as indicated in the protocol, and then click Go to print. A window should appear that gives you an opportunity to save the picture in a location of your choice on the hard drive. If no window appears, click Go a second time. Save your picture in a location on the hard drive where you can easily find it. If you would like a hard copy of your molecular picture, please see your professor or instructor. They can obtain one for you for your lab notebook.